A lot of gas samples are mixtures. They're not just a single gas. Air is a great example of a mixture of gases. So air is mostly nitrogen. It's actually 78% by volume nitrogen. It's got oxygen in there too, 21%. A little bit of argon, a little bit of carbon dioxide. Here we're talking about dry air as opposed to wet air. What's the difference between something being wet and dry? Water. So the air we're breathing right now, the humidity is fairly low. Oh, it just popped off on me. 52% is what the thing says here. But there is water vapor in the air. And if you've ever been somewhere really dry, like Death Valley or Phoenix, you just get parched. I mean, you just feel like your skin is drying out because the humidity might be down around 20%, right? And your body's not used to that. So here what we're talking about is air without any water in it. So dry air. We can treat a mixture of gases as if it was a single gas. We can measure, like for air, air's a mixture, but we can measure the pressure, the volume, the temperature as if it were a pure substance. If we calculate the moles then, we're going to get the total number of moles of each of the gases combined. So we get, if it says there's 5 moles, that means that the moles of nitrogen plus the moles of oxygen plus the moles of argon plus the moles of CO2 add up to 5. And we can do this because those gases in the mixture behave independently of each other. And the pressure and volume is only dependent on the moles of gas, not what it is. So if we look at the pressure of an individual gas in that mixture, that's called its partial pressure. Because one gas in a mixture is part of the whole thing, and so its pressure is part of the whole pressure. So it's a partial pressure. So we can calculate the partial pressure for a given gas in the mixture. The pressure would be equal to the number of moles of gas times the ideal gas constant times the temperature divided by the volume of the gas. Dalton's law of partial pressure tells us that if we take the partial pressures of all the gases in the mixture and we add them up, then we'll have the total pressure. This is how mass or weight works, like my box of bowling balls, right? If I had some 20-pound balls in there and some 10-pound balls in there, and I added up the mass of all of them, I would get the total mass. We don't usually talk about a partial mass, but we do talk about partial pressures. So the total pressure is the pressure from each of the individual gases. So here's math voodoo. So we've got that. The partial pressure of A is going to be the moles of A times RT over V. The ideal gas constant, the temperature, and the volume are the same for all of these gases because they're all in the same container, right? And so what they're doing here is they're factoring out the RT over V, and so then we find that the total pressure is equal to the total number of moles times RT over V, which is kind of what we said before.
Because the moles don't change.
Because what the particles are doesn't change anything.
Oh, 1 mole of helium and 1 mole of neon.
It's the same number of particles. Yeah. Yep. So we can look at the ratio of a partial pressure of one of those gases to the total pressure. And you can do all that junk. That ends up being the moles of A divided by the total number of moles. Because the pressure of a gas is directly related to how many moles of gas there are. This guy right here has a special name. It's called the mole fraction. And so that funny looking X is a Greek letter chi. So chi-A is NA over N total. It's like a percent, but we didn't multiply by 100. So then they do some more math, which I don't think anybody's really interested in, and we come up with this guy at the end. The partial pressure of one of the gases in the mixture is equal to the mole fraction of that gas times the total pressure. So if we have a 50-50 mixture of gases, right, then the mole fraction of the gas is 0.5. And so it's going to provide half of the pressure. So 0.5 times the total pressure. And the other gas will also do half the pressure. So the partial pressure of a gas in the mixture is the mole fraction multiplied by the total pressure. Yeah, so here we were looking earlier at percent by volume composition. Well, the mole fraction is the percent by volume divided by 100. So 0.78 times the total pressure. And so the pressure that nitrogen is exerting in air is 0.78 atmospheres. It is a lot. I don't want to do this example.
I'm already looking at it, I see what you gotta do.
There's just, I don't like this one.
Did you record already for this one? Tuesday, yesterday?
No, it'll be tomorrow.
What the hell is going on?
I think we're just to stop here. It's time to stop at 7:15. Class lecture's over.